Okay, so here's part 2 of the final exam review, things that did not make it into that first part. And just wanted to give you a few practice problems and film the thought process behind them so that you would be even more ready for your final exam coming up. And so here's some Unit 1 stuff that didn't make it in. We didn't have physical or chemical changes on that first review. And so again, for physical and chemical changes, the main difference between them is physical changes, we can return it back to its original state. So this would include warping the shape of it or changing different phases. Physical changes are not changing the chemical composition of that substance, whereas chemical, we are changing the chemical identity of it. So we are unable to get it to return it back into its original form. So taking a look at this, peeling an orange would be a physical change because we can put that orange peel back onto the orange. We didn't change the chemical identity of that orange peel. Lighting a candle is a chemical change. It is burning that wick at the top of the candle and combining oxygen and that carbon fuel into carbon dioxide and water, and so we cannot get it back into its original form. Barbecuing a steak, cooking meat, pretty much cooking anything, cooking eggs, cooking seafood, there's a change in color, there's a change in texture that we are unable to get returned back into its original form, and so that would be chemical change. Cutting a steak, however, is a physical change. And then freezing water, although it might seem a chemical change, we can return it back into its original, and so that would be physical change. We're just changing the state of it from liquid to solid water. Okay, accuracy and precision, when we're talking about sig figs, we mentioned how accuracy is how close you are to the actual answer, whereas precision is how sure you are of that answer. And so precision is another good word for precision in chemistry and math is consistency. Okay, consistency. How consistent is your data? How many decimals? Right. So if I have a number that's 0.0001 as opposed to 0.01. Okay, this number is more precise. When we're talking about lab data, however, if I have 3 data points, okay, this data is much more precise than, say, if I had 0.01, 0.05, 0.08. Okay, these numbers are much closer together, and so they're much more precise, much more consistent. And then of course accuracy, let's say that the actual answer was 0.06. Okay, these answers would actually be much more accurate because they're closer to the actual value. Alright, so that's the difference between accuracy and precision. We want both in chemistry and in science in general. Okay, classifying the following substances, we can classify it, and just to kind of draw the diagram again, we have all substances are broken up into either a pure substance or a mixture, more than one substance. Mixtures can either be homogeneous, in which it's all one composition, there's no layers, there's no stuff floating around, or it can be heterogeneous or heterogeneous. Okay, pure substances can either be elements or compounds. Pure elements or pure compounds. So taking a look at this, we have air. Okay, air is actually more than one compound, right? There's nitrogen in the air, there's CO2 in the air, there's oxygen in the air, okay, O2 in the air, and so that would be a mixture. What kind of mixture? Since it's all uniform, usually it's going to be homogeneous mixture. Okay, sand in a bucket of water, also a mixture. Okay, it's also a mixture. And in this case, because there's sand and water, there's 2 different things in there, 2 different phases, 2 different layers. It is a heterogeneous mixture. Copper, on the other hand, would be considered a pure substance. Okay, it's pure. Copper is only one thing, and it is an element. It's found on the periodic table. Okay, chlorine gas, Cl2, is also a pure substance. It's only chlorine. And so, but however, this would be considered a diatomic element. Diatomic element. We could also call it a molecule, okay, as opposed to an atom. However, it's not considered a compound because a compound is more than one element. Next is carbon dioxide, CO2. Again, because there's two different elements and there's a pure substance, but it would be considered a compound. And then water from the ocean, which has salt inside. Okay, that's going to be a mixture. And however, because it's one phase, unless there's like seaweed or other things we can see inside of the water, it's going to be homogeneous. Okay, homogeneous. Okay, also not on the original study guide was sig figs. We didn't have any sig figs on it, and so we're going to do that really quickly. So for sig figs, what we're looking for is counting. First of all, we have to count however many sig figs. That's very important. And so remember that the zeros are kind of where a sig figs gets a little bit tricky. If I have trailing zeros that there's a decimal and it's after a non-zero, they count. If I have zeros in front of a decimal, okay, like this one, never counts. Okay, or let me restate that. If I have a zero in front of a non-zero, they never count, never ever count. So even these ones never ever count. And then if I have trailing zeros after non-zero but there's no decimal, they also do not count. So a way that I heard from Mrs. Mitchell actually, that kind of makes it easy to figure out how many digits. Let's say we had the United States of America. Okay, what are the two oceans? We have Pacific and Atlantic Ocean. And so we can use this to figure out how many sig figs. And we're asking if there's a decimal. Is there a decimal? If it's present, we start from the Pacific Ocean. If it's absent, we start from the Atlantic Ocean. So here's kind of the trick. Notice, again, is there a decimal present? Okay, there is. So we're going to start here until we hit a non-zero, and then we start counting. So this would have 2. 1, 2. Okay, again, decimal present, so we start from here. Excuse me. Okay, and then we start counting, so 1 sig fig. Again, decimal present, so we start, we hit a non-zero right away. We start counting, so 3. Another decimal, so we go until we hit a non-zero. There's going to be 4. Now notice this one doesn't have a decimal, so we're going to start from the Atlantic Ocean and then start counting, so 3. No decimal, so we start from the Atlantic Ocean till we hit a non-zero, so 1. Okay, and so on and so forth. Decimal present, so there's 4. So this strategy is pretty helpful, okay, in figuring how many sig figs there are. Or you can just memorize the rules, right? Any zeros in a sandwich, they count. Trailing zeros only count if there's a decimal, and then zeros in front never ever count. So this one would have 5, this one would have 3, this one would have 4, and this one would have 3. Okay, now why that matters is because when we do calculations, we need to go with the least precise value, because that is going to be the value that we're least confident of. And so when we calculate, when we add or subtract, we go with the number with the least decimal places. When we multiply or divide, we're going to go with the least sig figs. Okay, or we're going to round to the least sig figs. So notice here, 3.4 minus 2.789 gives us this really big number, okay, 0.611. But since this number only has one decimal place, our answer can only have one decimal place. So I'm going to round it so that it only has one decimal place. So it's going to be 6.1 times 10 to the negative 1, or 0.61 would also be fine. Okay, next one, we have 0.0891 added to 0.03. Again, we get more decimal places than we need. Our answer should only have 2 decimal places. So I'm going to do 1.19 times 10 to the negative 1. Okay, our point. Now notice, if you didn't put into scientific notation, okay, and you had 0.119, okay, if you had 0.119, okay, and actually, let me see here. Actually, it still should, actually, no, it wouldn't work out. Okay, 0.119, right, has 3 decimal places, so you would need to do 0.12. Okay, you would need to round this digit up to 0.12. Okay. Multiplication. 300 times 390. Okay, gives us a really big number. Our answer can only have 1 sig fig. So this would be 1 times 10. That 3 rounds down. 1 times 10 to the 6. Okay, next one. 129.4 times 3, 200. Okay, again, I can only have 2 sig figs. So 4.1 times 10 to the 5. Okay, now if we I don't have an example here, I should have put one, but if you have multiple, like if you have multiplication and addition, okay, if we have multiplication and division, we're gonna have to round at each step and order of operations. So you would have to multiply first, round to correct sig figs, and then add or subtract, and then round to correct sig figs, rounding at each step. Okay, next example, 12 plus 0.031 plus 7.969. Okay, our answer can have 0 decimal places since we're adding, so it should be 20. Okay, and then next is 0.085 added to 0.062 added to 0.14. Our answer should only have 2 decimal places since we're adding, so 2.87 times 10 to the negative 1. Okay, if you had 0.287, you didn't use scientific notation, it should be 0.29. Okay. Alright, next is balancing reactions. Not sure why my arrows didn't show up. Okay, balancing chemical reactions, making sure that there's the same amount on each side. Hopefully by now this is pretty easy for you, but just some strategies. If there's an odd number of something, I usually just double it right away, because I know that this side it has to be an even number of oxygens. Alright, so, and then I start balancing. Notice that there's 4 hydrogens, so I'm going to make 4 hydrogens on this side, and then there's 4 oxygens on this side, 2 oxygens here, and then 2 oxygens here because of the 2 coefficient. So that's good. 2, 1, 2. Next one, let's see, looking for something to balance. Notice odd number of oxygens, so I'm going to double that, and then double this. Okay, balance that out. Next one. This one's a little bit more tricky because there's multiple things going on. The thing I noticed right away is that there's 2 NAs and there's also 2 H2s. So if I do that, that balances it. Now there's 2 carbons and 6 oxygens. Okay, and again I notice, there's odd number of oxygen, but there's another odd oxygen here, so that's fine. So since there's 2 carbons, 6 oxygens, I'm going to double this to make 2 carbons. And then check my oxygens, so I have 1, 2, 3, 4, 5, 6. Okay, 6 oxygens, so that's good. 1, 2, 1, 2. Okay, stoichiometry unit 4. So there was mole problems, but no stoichiometry problems, so I wanted to run through a few of those with you. And so number 1 is a stoichiometry problems, not a limiting reactant problem. Just asking for how many grams of hydrogen to react with 50 grams of nitrogen. So notice I have 50 grams of nitrogen. I want to find how much hydrogen I would need to react with that. So basically I have to get my 50 grams of nitrogen into grams of hydrogen. Okay, again, to review, mole heart. Okay, we can get grams, we can get molecules or particles, and we can get liters of a gas. So in this case, I have 50 grams of N2. So grams of N2 goes on bottom. I have to get into moles of N2. Then from moles of N2, I have to use what's called the mole ratio. Moles of N2 to moles of H2. And then moles of H2 to grams of H2. Okay, so these guys are molar masses. So if I look at my periodic table, put it up here. Okay, periodic table, nitrogen is right here. It's 14. Hydrogen is 1, but there's 2 of them. Okay, so for this molar mass, moles is always going to be 1. Notice I have another molar mass over here. And then for this guy, that's a mole ratio, mole over mole. That is the most important part of stoichiometry. It's like the bridge to get between different elements. The most useful part, mole ratio, moles over moles. So for that, I look at the coefficients. So H2 is 3, and then N2 is 1. Okay, so I'm going to calculate this, and this is going to give me how much hydrogen I need to react with 50 grams. So 50 divided by 14 times 3 times 2. Okay, so that would give me 21.4. Okay, 21.4 grams of H2. Okay. Okay, next, limiting reactant. Okay, so same reaction. Notice for this one I'm given 10 grams of each reactant. So 10 grams of H2, 10 grams of N2. Okay, so what I'm going to do is I'm going to turn both of them into the product NH3. So 10 grams of N2, and I'm going to see which one produces less than H3. That's going to be my limiting reactant. That's going to be the thing that runs out first. And 2 moles of N2. I want to get into moles of NH3. And then grams of NH3. And then same thing for oxygen. Or not oxygen, hydrogen. I'm going to get it into moles of NH3. And then grams of NH3. Okay, so from the last problem, molar masses, whoops, and actually I might have messed up on the last problem because molar mass is not 14, it's 28 because nitrogen is 14, but there's 2 of them. Whoops. So let me recalculate that real quick. So 50 divided by 28 times 3 times 2. So that would give me 10.7. Yeah, that sounds a little bit better. 10.7 grams of H2. Okay, 10.7 grams of H2. So this guy should be 28. 1. Okay, mole ratio over here. So I'm going to look for the coefficient. So NH3 is 2. And then N2 is 1. H2 is 3. Okay, and then grams of NH3, N is 14, and then there's 3 hydrogens, so 17. Okay, so I'm going to do this big calculation. So 10 divided by 28 times 2 times 17 gives me 12.1 grams of NH3 if I started off with 10 grams of N2. And then if I did 10 divided by 2 times 2 over 3 times 17, I get 56.7 grams of NH3. So notice what this tells me is that if I started off with 10 grams of each of these guys in separate reactions, okay, the nitrogen would make only 12.1 grams of it, of ammonia, whereas my 10 grams of hydrogen would produce a lot more ammonia. So my nitrogen is my limiting reactant, hydrogen is my excess reactant. Okay, I'm going to have leftovers of it. And the question is, how much excess? Okay, so to calculate how much excess, I'm going to take my limiting reactant and turn it into H2 to see how much of it would actually react. So I'm going to take my 12.1 grams of NH3 and kind of go backwards. So grams into moles, 17 moles of NH3 into moles of H2. So that would be 3 over 2 times mole of H2 and grams of H2. So 2 and 1. Okay, so let's see, 12.1 divided by 17 times 3 over 2 times 2 would give me 2.1. Well, that's really a little bit. Okay, 2.1 grams of H2, and this is how much would be used. Okay, remember we would start off with 10 grams, only 2.1 of it was used, so how do I get that? So 10 minus 2.1 would give me my excess. What is that? 7.9. 10 minus 2.1, 7.9. 7.9 grams of excess H2. Okay, so N2 is my limiting reactant, H2 is my excess reactant. I would have 7.9 left over. And then the last thing is, okay, let's say the student does this in real life and only gets 9 grams of it. What is the percent yield? So percent yield would be my actual over theoretical. Okay, so 9 grams, we actually produce 9 grams of it over 12.1 grams of it times 100. So 9 divided by 12.1 times 100% would give me 74.3%. 74.3%. Okay. Of course, it's almost impossible to get 100% yield. Usually we spill some, or some of it leaks out, or some of it doesn't react. 74.3 is not bad. Okay, so that's a stoichiometry problem. Lots there. I only have like 1 or 2 of those on the final exam. Okay, moving on. Same reaction. Okay, except this time I have 30 grams of N2 and 15 grams of H2. Okay, again, which one is going to be my limiting reactant? So I'm going to do 30 grams of N2, grams of N2, moles of N2, moles of N2, moles of NH3, moles of NH3, grams of NH3. And then I'm also on 15 grams of H2, turn it into NH3. Moles of H2, moles of NH3. Remember that the unit that you want goes on top for these kind of problems. So eventually I want to end up with grams of NH3. So same setup, molar mass is 17 for NH3. Molar mass is, whoops, almost made the same mistake, 28 for nitrogen and 2 for hydrogen. Mole ratio is 1 to 2 and 2 to 3. Okay, so I'm going to do this calculation, see which one is smaller. 30 divided by 28 times 2 times 17. 36.4 grams. Okay, and this one, 15 over 2 times 2 over 3 times 17, 85. Okay, so again, in this problem, which one produced less? My N2 is my limiting reactant. Hydrogen is excess. Oops, spelled that wrong. Okay, and then how much excess? I'm going to take my limiting reactant, or the amount that I produce with my limiting reactant, and turn it into hydrogen, into my excess reactant or excess reagent, and moles of H2 into grams of H2. So 2, 1, 1, 17. Mole ratio is 3 to 2. So let's see, 36.4 divided by 17 times 3 over 2 times 2. Give me 6.42 grams of H2. Okay, so I started off with 15. I'm going to subtract 6.42 grams. So my excess amount would be 15 minus 6.42. I'm going to have 8.58 grams left over in excess. Okay, unreacted. And again, let's say that student completes this reaction, only gets 5 grams of NH3. That's the actual value, so 5 grams, remember it's actual over theoretical, so 36.4 grams. Okay, so 5 over 36.4 times 100, okay, would give us 13.7%. Okay, 13.7%. Okay, 13.7% yield, which is pretty bad, but that's okay. Okay, so that's stoichiometry. Unit 5 and 6, light equations and nuclear chemistry. Remember that we give you the equations for this on the back of your periodic table, so let me show you where that is. Let's see here, put it over here since. Okay, so if I zoom in, let's see, where are you guys? Right here. Okay, these are the light equations. Right here. Okay, c is the speed of light, and I think the value is right underneath it. Yeah, c is right here, h is given to you as well. This is lambda, which is wavelength. Kind of looks like a wavelength. And then that v is actually the letter nu in Greek, or n, and that's the frequency in hertz. H is Planck's constant, which is 6.626 times 10 to the negative 34. Okay, and that's all you really need for these problems. So we have a photon with a frequency of that much. You want to calculate its energy, so we're looking for E. E is equal to Planck's constant times nu, which is a frequency. 6.626 times 10 to the negative 34 joules per second. Okay, multiplied by 2.68 times 10 to the 6 hertz. Hertz is actually 1 over second. Okay, and that's going to give us our energy. So let's see, 6.626 E negative 34. I'm going to multiply that by 2.68 E6. Okay, that's going to give me 1.78 times 10 to the negative 27 joules. Okay, joules. Okay, calculate energy and wavelength of a photon. Okay, so energy again, Planck's constant 6.626 times 10 to the negative 34 joules per second. Let me just make sure it's 34. Yeah, 34. Okay, and I'm going to multiply that by the frequency, which this time is 6.1. 65 times 10 to the 14 hertz, 1 over a second. Notice that the seconds will cancel, and we're left with joules. And so energy would be equal to 6.626 e negative 34 times by 6.165 e to the 14. Okay, so that's going to be 4.08 times 10 to the negative 19 joules. Okay, so that's how much energy. We want wavelength, so we're going to have to use that other equation. So I'm going to use C is equal to, actually we know what C is. 3 times 10 to the 8 is equal to the wavelength times the frequency. So frequency again was 6.165 times 10 to the 14th hertz. Okay, so divide both sides by or divide the frequency to get wavelength by itself. So I'm going to do 3e8 over 6.165 to the 14th power. So my wavelength is going to be 4.87 times 10 to the negative 7 meters. Okay, it's always going to be meters. So if it's not in meters, got to get into meters. Okay, so like, yeah, for example, this one. So frequency and energy of blue light that has a wavelength of 4 nanometers. Remember, nano is times 10 to the negative 9th power. So I'm going to do frequency first. So I'm going to use the light equation. Is equal to, okay, this is the wavelength, so 400 times 10 to the negative 9th. And for now, I'm just going to do it like that because it'll be easy to put in my calculator. Of course, that is incorrect scientific notation. Okay, I'm solving for nu. Nu is equal to 3e8 divided by, put in parentheses, 400 e negative 9. Okay, so I'm going to get 7.5 times 10 to the 14 hertz. Okay, here's my frequency. And then from that, I can calculate my energy. Energy is equal to Planck's constant multiplied by the frequency that I just got. Hertz and joules per second. So I'm going to have 6.626 e to the negative 34 multiplied by 7.5 e to the 14. And so E is going to be equal to 4.97 times 10 to the negative 19 joules. Okay, next we're going to be balancing these nuclear reactions. Remember that the options are, we have alpha, which is actually a helium particle. We got beta, which is actually an electron. We have gamma, which is massless. And then sometimes we also have a positron. Okay, so for this one, we're looking for x, and we have to balance these numbers with these numbers. So I have to get 3 on top. So how to get 3? Well, it's going to be a 3 here. And then how do I get 1 from a negative 1? Well, it has to be a 2. Okay, so 3 over 2. Notice that this is a beta particle, and it's in the products, is to the right of the arrow. So it is beta decay. If it was in the reactants, if the radioactive particle was in the reactants, if it was on this side, then it would be capture. Okay, and from this we could figure out what the identity of this element is. Let's see, 3 over 2. So again, the 2 is what's important, is the identity of the element. So this would be a helium. Okay, this would be helium. Okay, this 2 is important. The 3 doesn't determine the element, it's the atomic number. Okay, again, we're looking for this, so let's see, how do I get 232 from this? Well, this has to be 4. 4 plus 228 is 232, and it has to be 2. So notice this follows an alpha particle, so I can change this to an alpha, or helium. So this is alpha decay. Okay, the next one, notice that top doesn't change. This one has to subtract to get to 58. So 0, -1, this is a beta decay. Okay, this one, solving for x, 0, so this doesn't change. +1, so what +1 gives you 30? 29. Okay, so again, I can kind of, this is a positron decay, because it's a positive, negative is an electron. And then 65, 29, 29 would be copper. Okay, so this is actually copper. Okay, last one. So the top number is 0, bottom number is a +1, so this is also positron decay. Okay, periodic table, unit 7. We didn't cover the trends, so I'm going to go over the trends with you real quick. The biggest element on the periodic table is Big Frank. Smallest one is tiny fluorine. So atomic size increases as you go down and to the right, or sorry, down and to the left. Okay, the closer you get to francium, the bigger the element is. The closer you get to fluorine, the smaller it is. Atomic radius is all about size. Okay, and if you can remember that, Big Frank and small fluorine, the rest are opposite. Okay, for ionization energy, and I'll do it in a different color, for ionization energy, it increases as you go up and to the left, or sorry, to the right. Okay, ionization and electronegativity. Okay, ionization energy is energy needed to take an electron. Electronegativity is its ability to attract an electron. Okay, or how bad, I like to think of it as how badly it wants an electron. And so for electronegativity, fluorine is the biggest, has the highest electronegativity. For ionization energy, however, the highest is helium, because helium is a noble gas. It has 8 valence electrons. It doesn't want to give up any electrons. It's stable. And again, all the elements want to become like these noble gases here. So they're either going to give away electrons, like lithium will give away an electron, right? It has 1 valence electron, so if it gives it away, it'll become like helium. So that's why its charge is +1, because it usually gives away 1 electron. Beryllium's group is +2 because it gives away 2 electrons. Fluorine's column is -1 because it wants to take 1 electron to become like a noble gas. Okay, and then the last question that didn't make it onto the final exam, or the final exam review, intermolecular forces. Remember, inter means between molecules, not in, as opposed to intra. Like intramurals would be inside the molecule, so intra would be covalent bonds. We have ionic bonds, metallic bonds. Okay, so we're not talking about those, we're talking about intermolecular forces. And it all depends upon polarity, mostly. Okay, if it's non-polar, it's going to have dispersion forces, which is also called London forces. It's also called van der Waals. There's a lot of names for them, van der Waals forces. Okay, it's the weakest kind of intermolecular force. If it's polar, then it's going to have a dipole-dipole, which means that there's a positive and a negative end that is attracted to another positive and negative end of another molecule. And then sometimes we have a special type of polar bond, the strongest type of intermolecular force, if the molecule has an H, F, O, or N, H phone. Okay, H phone. So looking at these guys, if I were just to draw methane real quick, notice that it has rotational symmetry. If I rotate it 90 degrees, it's the same thing. And so it is nonpolar, which means that it would have dispersion forces. Okay, so if it can rotate, if it has rotational symmetry, dispersion forces. H2O. Okay, H2O, since it has lone pairs on the middle, it's polar. And it's a special type of polar. It has a hydrogen and an oxygen in it. So it's, and sorry, let me rephrase that. It's if a hydrogen is bonded to one of these three. So if a hydrogen is bonded to fluorine, or hydrogen is bonded to oxygen, or hydrogen is bonded to nitrogen, then it will have a hydrogen bond. So this, of course, would be hydrogen bond. And then HF, okay, notice that would also be hydrogen bond. Okay. So let's see, what's one that would, let's say we had sulfate. Okay, this is sulfate. Notice that this is polar. It's not symmetrical. Okay, lone pairs. And so because of that, and notice it has an oxygen, but it's not bonded to any hydrogens. So this would have dipole-dipole. Okay, so there you have the example of each. All right, so that's it for this second part of the final exam review. Thanks so much for joining us and taking the time to study. Good luck on your study.